what exactly the spontaneous mean based on the concept we learned before? In the earlier chapter, when we discussed the reaction quotient compared with K, and when the Q is less than K, that means you have too much reactant, because reactant as denominator in the calculation quotient. Too much reaction shift to right, shift to getting more product. And that is, we call this reaction spontaneous, because from the reactant become product. It happens when you have this reaction shift to right, or spontaneous. If the quotient too large, quotient larger than K, as we predict on the equilibrium chapter, Q larger than K means the reaction will shift to left. That means the forward process non-spontaneous. Forward non-spontaneous. It will shift to left. So from the reactant become product non-spontaneous. From product become reactant, it actually become spontaneous. Q equals K means the reaction equilibrium, and the delta G should equal 0. And so from this, we get a new equation. This is a non-standard free energy change. Okay, it's not the delta G naught. The non-standard free energy change, it is basically how much driving force from the given status to the final equilibrium. Final equilibrium, we have this equation. And so when the Q and K are very different, you get a ratio either very large or very small. The delta G is either very negative or very positive. Means the reaction not equilibrium. Reaction is not equilibrium. It will still proceed to reach equilibrium, and along the way, either give away free energy, do useful work, or absorb free energy. So either these two. If the Q close to K, that means the system not far from equilibrium, and not so much work can be involved, either lost or gained. Not so much free energy change can be involved. So anyway, this is get to the final end point. The standard free energy and the equilibrium constant Kp. The Kp, as you remember, it is the equilibrium constant based on the partial pressure for gas, Kp. Previous calculation in the equilibrium chapter or the acid-base chapter, we've been always using Kc, because we have not really deal with an equation that has gas. But theoretically, the free energy change, standard free energy change, it is related to the equilibrium constant Kp. And here's the equation. Negative RT, the T is the Kelvin temperature, R is 8.314. This is the same constant in the Arrhenius equation. It's the same R as in the Arrhenius equation. So basically, the very large delta G, very positive delta G, it means, because negative, it corresponds to very small equilibrium constant. And very small equilibrium constant, the constant smaller than 1, means the equilibrium favor reactant and not favor product. If the delta G is a very large negative, that means K is very large positive, highly favor the product. So what I've been talking about, the spontaneity, the spontaneous reaction, it actually means once the system reaches equilibrium, the product is highly favored. Or very large K, large Kp. And also, if we know the free energy change, we can calculate the equilibrium constant, Kp. We can calculate Kp. And vice versa. If we know the Kp, we know the temperature, we can find the free energy change. So finally, the equilibrium chapter and the energy, there's a connection. And that's the equation between the equilibrium constant and free energy change. And also keep in mind, this equals the enthalpy change minus temperature and the entropy change. These all come together. And for the non-standard free energy change, this is a non-standard free energy change. That meaning may not be at equilibrium. It's non-standard. Non-standard free energy change depends on the reaction quotient. The substance at the standard conditions, at 1 atmosphere for the partial pressure of the gas, or 298 degree Kelvin, or the solution is 1 molar. These are standard conditions. Standard condition quotient equals 1, because everything, the concentration or partial pressure, or the temperature, all make that quotient equals 1. The non-standard conditions, when you have a system, maybe not the standard condition, that delta G, it is the standard free energy change. This is the calculate the standard enthalpy change minus to calculate this. You use the standard enthalpy change and entropy change, the standard free energy change, plus the RT times natural log of the quotient P. So quotient P means for gas, we need to use the partial pressure of gas to calculate the quotient. So this slide, we have 2 equations. One is for between the standard free energy change and the equilibrium constant. The second one is when you have a non-standard conditions, the free energy change. Use the quotient. And when the QP equals 1, by the way, if QP equals 1, that's when everything's in standard state. Then the delta G is equals delta G naught, delta G 0. So that's the difference between the standard free energy change and non-standard free energy change. The standard free energy change, it helps us predict is this reaction spontaneous or non-spontaneous. In other words, the delta G, it tells us how is the K relative to 1. The delta G naught is telling us how is this compared with 1. Is K larger than 1 or less than 1? That's the standard free energy tells you. The non-standard free energy, delta G, it tells us positive or negative. It tells us, is this system from the given status, maybe not standard condition, how that will move? Will shift to right or left? So calculate the delta G in non-standard. It is same as we should get the same results as we discussed earlier, compare quotient versus equilibrium constant. Delta G is delta G is negative, means the equilibrium shift to right. Positive shift to left. And that's the same as we discussed the quotient. It is the same, give the same discussion, give same results. The difference is now we have energy measure instead of just compare value and qualitatively talk about left and right. Now we have energy. This is energy positive, negative. Okay, any questions? So remember the difference, they are the concept difference. The delta G, the non-standard, is predict how the equilibrium shift or left or right. The standard G, it tells us the K. It actually tells us how the K is a product favorite or reactant favorite. And so because that equation, the delta G equals negative RT. You can see the value of the delta G is correlated to the equilibrium constant. And each one at a room temperature, the temperature maintains the same. So you can see the a very positive delta G means reaction non-spontaneous, which actually means the equilibrium constant very, very small. And the very negative delta G means a very large equilibrium constant, highly favors the product. So the spontaneous reaction or not, and if you consider in terms of equilibrium, as we know, almost all the reactions are reversible. All of them are the equilibrium, the results of equilibrium. And so delta G is only shows us how much, what is the position of equilibrium? Is it finally in the highly favors the product or still remains a reactant? And delta G is related to K, Kp. So calculate the K at 2 temperatures. This is an example how we use the free energy change to calculate equilibrium constant. And this equation we have the standard free energy change. With this equation to solve for Kp, let's divide by negative RT first. And then we solve Kp, we raise to the exponential on both. And that equals Kp. So basically Kp equals this. This equation somehow resembles the Arrhenius equation, kind of similar. So simply just use the delta G value given the question and use this to find out Kp. So let's do the one by one. Let's do the first one, the 298 Kelvin. 298 Kelvin, what we get is Kp exponential of the at 298 Kelvin, the delta G is negative 141. So negative 141, 1.6. 0.6 kilojoule. And the R is 8.314. The unit is in joule. And then you times temperature is 298 Kelvin. So you can see the Kelvin get canceled. The mole canceled here. And finally, kilojoule divided by joule. To do that, I need to times 1,000. So let's just times 1,000 here. Joule over kilojoule. And that way the joule get canceled. Kilojoule is gone. Everything get canceled as a power, that's perfect. And so that's how you get the equilibrium constant at 298 Kelvin. Sig figs. This is exponential. So the number of decimal place in your exponent, it becomes number of sig figs in your decimal part. Okay, this is a rule we learned almost since day one. The number, it should be very large number. The exponent is 57.2 because sig figs, and you can see there's only one decimal place in the exponent. So final answer, keep one sig figs. Keep one sig figs. And the next temperature, 973. This is the 700 degrees Celsius as we calculate the free energy in the last practice. And at this time, the delta G, we calculate Kp. The exponent is 1.50, 3 sig figs, 2 decimals in the exponent. So final answer, in the decimal part, only 2 sig figs, 4.5. So you can see the both temperatures, reaction still spontaneous as the delta G's are negative for both. But the difference is for the delta G's, that's a more negative, very large negative numbers. K is much larger. And whereas the delta G is a very small negative, you still have a K is larger than 1, but not exponentially or astronomically large. It's just barely more than 1. So that's how the standard free energy change, delta G naught, relate to the equilibrium constant, Kp. And the next we'll do practice on the non-standard free energy change. So what about non-standard free energy change? That depends on quotient. That equation, non-standard free energy change, come from so we use this equation to calculate non-standard free energy change. And 2 containers. The 2 containers both have the same content, have the sulfur dioxide, oxygen gas, and sulfur trioxide. You have all three components in the equilibrium. The difference is one is 25 degrees, which is 298 Kelvin, and the other is 793 Kelvin degrees. The 973, which is 700 degrees Celsius. And so the question asks, in which direction will the reaction proceed? So basically ask about, will this reaction equilibrium shift to right or left at that temperature, given the condition, given the pressure of each component. So to answer that question, we need to first find out the reaction quotient, because we have everything that in the equilibrium. Each one has a concentration, has a pressure. So we can find the quotient. Since the question asks about predict how this reaction will shift to right or left, so we need to calculate non-standard free energy. And to do that, we have the standard free energy from the last slide. We're going to use that for combine with what we calculate here, the quotient. Together we predict. And so first we do the quotient. The quotient with this equilibrium, sulfur trioxide is a product. So we have a pressure of a sulfur trioxide. The coefficient 2, so it becomes square. Pressure of the concentration or pressure of the product divided by the reactant. And divided by the first reactant, sulfur dioxide. Sulfur dioxide, coefficient 2, so we put a square. Square of the sulfur dioxide pressure. And then we times the pressure of O2. So now just substitute with the number. We have sulfur trioxide, 0.100. The units, you can skip the unit because calculated quotient or equilibrium constant are dimensionless. We don't consider units. This is pressure for sulfur trioxide, a square. And sulfur dioxide is 0.500, 0.500. Should also have a square. And finally, the O2, dioxygen, is 0.0100. So you can easily calculate the quotient. Easily calculate quotient. The quotient, if I were to calculate, we have this. It should be 4.0 and 0. 366. So that's the quotient for this reaction. In which reaction will the reaction proceed to reach equilibrium? In the part C, it did not ask about delta G, and later you see the second question about the non-standard free energy chain, delta G. So for B, I don't have to use the non-standard free energy because that's the next question. Once you calculate quotient, you just need to compare with K. And the K at, according to backtrack to the last page, we find out K for both. These are Ks for the two temperatures. One is very large, and the other one is 4.5. So you can see for the B, I calculate quotient. This quotient, it is less than the equilibrium constant Kp at either temperature, 298 or 973 Kelvin degrees. Yeah, the 700 degrees or 25 degrees. I have the K. So either case, it is less than the Kp. So Q is less than K at both temperatures. That means in both cases, equilibrium shifts right. And so that's the conclusion based on just quotient compared with K. Well, the next question asks about the non-standard free energy change. So that is, we need to calculate the actual non-standard free energy change. And we have two temperatures. So each temperature we need to do separately. And let's just do the room temperature, the 280 Kelvin. The one 298 Kelvin, the delta G naught at the 298 is a very negative number. Let's go back to the previous slide. Where is that? There we go. This is the room temperature value for this reaction, negative 141.6. All right. So I put in here negative negative 141.6. This is standard free energy change at this temperature. So the non-standard free energy change, I use the standard, which is negative 141.6. And the units, I think I don't need a mole. I don't need a mole here, so I don't need a mole. And time plus the R is 8.314. This is in joule, so we need to convert to kilojoule. Times temperature is 298 Kelvin times natural log of the QP. QP is 4.0. And so far I'm getting this is okay here. Sometimes I kind of losing track of the units for the R. The R has units. It's actually JK, Joule, K, and mole. The mole actually is not, it's always just the same mole based on what the equation is. In this equation, we have 2 moles of sulfur dioxide. And so this results, the delta G, it is for 2 moles of sulfur dioxide. So anyway, doing this, we just need to convert the kilojoule. And then your problem solved. You should still get a very small number, very negative number. So that is agree with the prediction. When you have a very negative number, what you get is still a negative number because this reaction should highly favor the, will shift to the right, will shift to right. It will, same prediction as we predict for the, according to B with the reaction quotient. If you do the 700 degrees Celsius, the calculation is almost exactly the same. The difference is you have a different standard free energy change, and you have different temperature. So the numbers are different, and we have those numbers calculated. So you can see 700 degrees is non-standard free energy. It is a very small non-standard. Non-standard. I keep adding a not. The non-standard free energy is negative 0.9. That's a very small negative, which means it will shift to right, but the location is not very far from the equilibrium. Is given such a small non-standard free energy change. And it makes sense because the quotient equals 4 and the K is equals 4.5. They're very close. It will need just some small movement to shift to reach equilibrium. So that's how we use the to calculate standard free energy change, equilibrium constant, and then use a quotient and standard energy change, free energy change, to find non-standard. The non-standards, it is supposed to help predict if the reaction shifts right or left. And finally, exactly what does it mean? This is the reaction progress. We start from the pure reactant. This is the reactant. The left hand is reactant, and right hand is the product. Supposedly, the reaction should complete, become product. But when you have a situation in the final stage, you have 100% product and 0% reactant. This is actually not stable, because the actual reaction is always reversible. Once accumulated high enough product concentration, it will reverse back to become reactant. So the reality should always be is an equilibrium between the reactant and product. And the delta G naught, the standard free energy change, is supposed to be meaning the energy difference between these two. This is standard free energy change. So start from the pure reactant, and once you get a pure product, no mix, you get a pure product, the energy difference is such. But the reality is, any reaction reaches to a point when you have enough product, then the product reverse to give you a reactant. So in the real system, there are always some reactant or some product mixed with the others. And for that kind of mixture, how this mixture will shift right or left, it is actually, you need to consider the quotient. When your quotients, this is the situation, quotient small, it will progress to reach final destination, the equilibrium point. So on the left-hand side are the, you have abundant reactant and not enough product to reverse the reaction. Reaction will shift to right. If your reaction mixture belongs here, this is the location we have a pure, almost pure, close to pure product, but no reactant. And so the reverse reaction rate is highest, which means some of the product will reverse. If your reaction mixture, the quotient shows you are in this area, then those mixture will shift to left, produce some reactant, and then finally reach equilibrium. So the difference between the standard free energy change, the delta G is 0, whereas delta G is different. Yeah, the delta G 0 is the absolute difference between the pure reactant, pure product. And delta G is when you have mixtures, some random mixture, we don't know how it will shift right or left. That is actually when you calculate, use the equation to calculate. For any reaction, eventually it will reach a equilibrium. You will not get a pure product in this case. Or in the second slide, you can see the second slide, the right-hand slide graph shows you the product of a high free energy, which means the reactions should be non-spontaneous. Even for non-spontaneous, it will produce some product. And so the reaction rate between forward and reverse equals, which means equilibrium. And we're getting close to the end. There's a couple more concepts. In biology system, there are many reactions in the biological system, and they have enzymes as catalysts. So the reaction fairly smooth and easy, smooth. But there are some reactions give a huge amount or release a huge amount of free energy. This free energy can be used by the nearby tissues, organs, structures to carry out their own reaction, even though those reactions may be very difficult to progress. That's where the in biological systems, there are many reactions highly spontaneous, which means highly forward product favored and release energy. Those process, if close to a non-spontaneous process together, then the spontaneous can give the energy and make the non-spontaneous happen. This we call a coupled reaction. So for example, in the cell, a DNA replication or the manufacture of proteins, those are highly non-spontaneous reactions, because to make protein from amino acid, it is a entropy decrease process, and also is a exothermic reaction. It's exothermic reaction, but entropy is decreasing because it starts from tiny each individual amino acid and becomes organized protein molecules. Is not spontaneous. How to make that happen? In the cell, there's ATP and ADP. They release the free energy. When they react with water and release a phosphate ion, they release a huge amount of free energy. And this energy, if nearby those reactions, the non-spontaneous reaction in the cell, it can make those reactions happen. So in a way, it's basically the ATP-ADP reaction, it gives free energy. It gives free energy to force those non-spontaneous reactions to take place. Okay, I think that's the end of a chapter. We're done for the free energy